So we're going to look at this communication link. It is a wavelength of 1,550 nanometers, 1550. This is sometimes called an eye-safe laser. That's incorrect. There's no such thing as an eye-safe laser unless it is below, the output is below the MPE. Then it's eye-safe, but that holds for any laser. 1550 is an eye-safer wavelength to work with. That's because it's absorbed by the entire volume of your eye and is not a retinal hazard. Okay, so 1550 is eye safer, but it is not eye safe. I worked with a laser that was, it was a YAG. We had an OPO on it, changed it to 1547. This was a Q-switched pulse, and yeah, you do the analysis on that laser and you find that for 1547 Q switching, it was by no means safe to look at all. So there is no such thing as an eye safe laser unless it is below, the output is below the MPE. So we have a 1550 wavelength. It is continuous wave. We have an average power of 200 milliwatts. We're using the ANSI default for an infrared exposure of 10 seconds, 1 over E squared, circular Gaussian, and look at this, 33.87, almost 34 millimeter diameter beam, and that's because a 2-inch or 50.8 millimeter diameter telescope is being used as a beam expander. Right? And we're using this as a communication link over a long distance. We need to keep that beam as small as possible over a long distance. In other words, we want the highest radiance at distance that we can get. We know to take that aperture of the telescope, 50.8, divide it by 1.5. That's how we get this diameter. Well, let's quickly check that out because we can do that. Let's turn on optically aided viewing, okay, and we'll come and look at our extended features. We'll go here. We will say, well, we want 50.8. We're going to change this. Well, that should be 70. Look at that. Yeah, that's a little bit of math variation in the math, right? So that's reporting almost 70%. So there's a calculation going on there that gives us that. And let me just change that to 100%, and then we'll say OK. And then we look at our transmission through this user-defined limiting aperture, and it's about 99%. That's our 99% criteria. It's met. We're good with that. Let's go back and change this back to the default parameters that we're using, and we'll hit default, and there it is, and it says OK. All right. Oh, and let's turn optically aided viewing off. We don't need that. We'll say no. Okay. So we have, based on, we've set the m-squared diffraction to 1 as a default for a conservative approach to this analysis. That gives us a divergence of about 58 microradians, so a very low divergence, and of course that has to do with an m-squared of 1, and assuming that the beam diameter at range, the beam waist diameter is almost 34 millimeters. Something I'm going to point out here, and I know that we have an NOHD of 0, but let me just say this. When you're using a beam expander, the NOHD is calculated or is reported. That distance is from the beam waist. And normally, without a beam expander, your beam waist is very close to your the output aperture of the laser, typically. And the NOHD is so long that it doesn't matter. We just say, yeah, the NOHD, we give you an NOHD of 200 meters, and we're really kind of saying that's being referenced from the output aperture of the laser, okay? And in most cases, that's okay. Sometimes it's not. And a case is when you're using a beam expander, because a beam expander will push that beam waist way out. That's the whole point of it. Now, I won't get too far into how to determine where the waist is, But in some cases, it's pushed out tens of meters or 100 meters. Now, a lot of times, again, even if it's pushed out 100 meters, as with a rangefinder where we're looking at an NOHD of, 10, 15, 20 kilometers, 100 meters doesn't matter. We just go ahead and say, well, your NOHD is so long. It doesn't matter whether you reference it from the beam waist or the output aperture of the beam expander. But if you were running low power, where your NOHD was, say, 50 meters, and you'd pushed your beam waist out 50 meters, all right, and you were telling your user what the nominal ocular hazard distance is, you have to remember that the assumption sort of is it's from the output aperture, okay, that measure. So what would you tell your user? Well, I would tell the user that the NOHD from the output aperture of the beam expander is 100 meters, all right, not 50, but 100. And that's because, oh, wait, I've got to add the NOHD on to where the beam waist is located. Okay, and as I said, most of the time it kind of goes without being said that we're always referencing the output aperture of the laser when we're talking about distances such as the NOHD. And most times it doesn't matter, but sometimes it does, so we need to think about that. Okay. Let's go through this. We have an observer range of 1/4 meter. Let's set this to 1/2. That's really where we kind of like to set up at. OD at observer range. Let's do diffuse reflection. Go to our standard 1/4 here. Okay, so at 1/2 meter, we have the same beam diameter as what we started out with. That's 50 microradian. 58 microradian divergence. You're not going to get any change in the beam diameter over that kind of distance. And look at this. There's no OD at observer range. What we're reporting is the fraction of the MPE. So instead of an OD, what we're saying is, well, you're at a fraction of the MPE. And we report this so you know how close to the MPE we are. All right. So in this case, we're under 50% of the MPE. The worst case OD is 1.32. All right, and that's if magically we were able to get all the power through the limiting aperture, which is 3.5 for the eye, and it's the same for the skin, 3.5. We look at the NOHD, we have 0, and we can guess what the NSHD is going to be. It's going to be 0 too, because same limiting apertures, same MPEs. If we don't have an NOHD, we certainly aren't going to have an NSHD, are we? No. All right, so let's set that back, and the MPEs are the same as 0.1 watts per square centimeter or 100 milliwatts per square centimeter. And we're assuming that what's going on here is the absorber is the same, and it's basically sort of water absorption going on here. All right, times skin MPE. Well, we know it's under 1 because we've already looked at the NSHD. That's 0, so we know the times skin MPE is less than 1, so there's no skin hazard, there's no eye hazard. To this laser running 200 milliwatts, 1550 with this large of a beam. You can look at the diffuse reflection information here. There's no source type because we are outside the retinal hazard region. And there's nothing special going on here. The NHC is about 8 millimeters, so we wouldn't there's no realistically there's no NHC, there's no OD at observer range, and everything is the same for the skin. All right, but now before we put this beam into that beam expander, let's take a look at that beam. It was a 2 millimeter beam, let's say. So we'll go 2 millimeters and we'll do 1 for m squared, and we can see, yeah, this makes sense. Notice that there's a slight difference here, okay, and that's because it's a 2 millimeter beam passing through a 3.5 millimeter diameter aperture that we're passing almost 100%, but not quite, and that's the difference in these two numbers. We now have an NOHD of 22.5. What would be the NSHD? Well, it's going to, of course, be the same. All right, and we can see that now we have a potential skin hazard with this beam. It is the times skin MPE for the intrabeam skin exposure is 20.7. Again, 200 milliwatts, there's a lot of the volume of your tissue absorbing this energy. So although you may feel it, it's not going to be anything that is going to be much of an issue to you, other than you'll feel it and you'll move. Okay, but it's certainly not life-threatening or something that you would say, well, if it was a 10-watt visible beam, that's clearly a hazard. In this case, this is we are above 1. It is a bit of a skin hazard, but not something that we would be terribly concerned with. What would we say to the user? Be careful. All right. What about working with a small beam? Would we just say be careful with it? No, we would not just say be careful. We're going to put eyewear on the user, because 1.30D, it is a hazard. And this laser is a hazard for 22 meters when you're working with a small beam. All right. What else? Oh, we have a fiber optic here. Let's take a look at that fiber optic. Now, this is a single mode fiber optic. It is 9 micron fiber, but because we're working in nanometers, this is also controlled by the switch. Now, what I would say is, if you said, well, I'm not real good with math and exponents and things like that, 9 microns, I'd just like to put it in as 9 microns. So go up here, switch this to micron, and then you can input it as 9, and then if you want to, you can come back up and switch it to nanometers, and it does the switch. Okay, so we see that the fiber optic NOHD is about 10 centimeters. That's all it is. And if we had a reasonable observer range, oh, we do. Sorry, I was looking at the 0. The observer range is 1/4 of a meter, so you don't have an OD at observer range here at all. And even if we put 10 centimeters in here, which would be the closest we would do the analysis, okay, don't think anybody would ever get up any closer than that. Now, this is not in the retinal hazard region, so this idea of how close you get it is really subjective. You may want to put a 0 in here saying, well, somebody could stick it right up to their eye, right? That'll be the smallest beam and the worst hazard. But typically people don't do that, particularly when they're trained, and professional folks don't do things like that, bring a fiber right up, okay? So we'll stick with 1/4 of a meter. So, you'll notice here where we are reporting the irradiance at observer range in 1/E of the actual beam. We can see that for this small beam, we have an irradiance in the beam in 1/E squared. If at 1/2 meter is 12 watts per square centimeter. If for some reason you had this and you were going to put up a barrier and say it was probably 1.5 meters away, you'd see you don't have a high irradiance, 0.8, a little over 8 watts per square centimeter, but we are also reporting the fiber optic, okay, and that's based on this number. Now, can we reproduce this up here? Yeah, we can, because we know that the mode fill diameter is considered the 1/E squared sort of beam waist, and then we know that for a single mode fiber, we would express this with an m squared of 1. So let's check that out. 9 micron, that would be 0.009. And then we'll stick with m squared of 1. And what do we have? We have an NOHD of 0.1. We have an NOHD of 0.1. Let's put our observer range at the same distance here, 0.25, and we'll see that in the irradiance in 1/E squared of the beam, these work out the same. So you can see that we can duplicate this up here in the intrabeam section as well. Okay? All right. I think that's about it.